Bună dimineața! Se aude?
Domnule ambasador, eu Excelența voastră, stimate domnule ambasador Yoshihiro Katayama, dragi elevi, studenți, doctoranzi, tineri cercetători, bună dimineața! Suntem în incinta Academiei de Științe a Moldovei, Sala Azurie, unde astăzi are deschiderea oficială a școlii de vară Inovații în nanomedicină. Este vorba de pregătire interdisciplinară la intersecția tehnologiilor moderne, a nanotehnologiilor cu biomedicină. În Sala Azurie sunt o parte din tineri și mult mai mulți sunt online. Și vă atrag atenția că prelegerile sunt transmise în format live stream și de către Institutul de Dezvoltare a Societății Informaționale și de Privesc Eu. Eu le aduc mulțumiri partenerilor pentru diseminarea largă a informației și cred că mulți studenți, elevi, tineri sunt acum online. Îl salutăm pe domnul ambasador, excelența sa, Yoshihiro Katayama, care dumnealui este un prieten al cercetătorilor științifici. Ambasada Japoniei ne-a susținut și ne susține. Avem colaborări foarte frumoase cu țara Soarelui Răsare și această colaborare se extinde și în cadrul școlilor de vară și de toamnă pe care le-am realizat și astăzi iarăși realizăm împreună. Am organizat și școli de vară moldo-japoneze în contextul conferinței internaționale în domeniul nanotehnologiilor și ingineriei biomedicale. Și, domnule ambasador, ăsta e proceedings, materiale conferinței a 5-a, care a avut loc în noiembrie 2021. Deci, materialele sunt deja publicate de către Springer. Avem lucrări comune cu colaboratori de la centrele de cercetare și universități din Japonia, foarte frumoase colaborări cu Universitatea din Shizuoka. Cu această universitate, Academiei de Științe are și un contract, un acord de colaborare și pe parcursul ultimilor ani avem o strânsă colaborare cu domnul profesor Hiroshi Amano, o personalitate de excepție, laureat al Premiului Nobel în fizică și Premiul Nobel i-a fost decernat pentru contribuții de excepție în dezvoltarea tehnologiilor de lumină. A elaborat primele LED-uri în baza nitrurii de galiu, care astăzi sunt fundamentul, reprezintă fundamentul dezvoltării tehnologiei luminii albe. Noi toți cunoaștem că sunt în implementare LED-urile de lumină albă foarte eficiente. Păi iată, grație eforturilor profesorului Hiroshi Amano de la Universitatea din Nagoya, Japonia, sunt succese remarcabile la scară internațională. Stimate domnule ambasador, noi la ora 9 vom ieși deja în direct cu Universitatea din Japonia, unde o să-l salutăm pe domnul profesor Hiroshi Amano. Vă rugăm să veniți cu un cuvânt de salut.
Stimate domnule președinte Tighineanu, președintele Academiei de Științe a Moldovei, stimate domnul profesor Amano, Universitatea din Nagoya, Japonia, stimați oaspeți, studenți, elevi și tineri cercetători din Republica Moldova. Dragi prieteni, am o deosebită plăcere să vă salut la deschiderea oficială a Școlii de vară cu genericul Inovații în nanomedicină, organizată în cadrul proiectului NanoMedTwin. Mai întâi de toate, permiteți-mi să aduc mulțumiri conducerii Academiei de Științe din Moldova pentru organizarea acestui eveniment și profesorului Hiroshi Amano din cadrul Universității din Nagoya, Japonia, pentru implicarea activă și ca urmare a împărtășirii cunoștințelor în domeniul nanomedicinii cu studenții și tineri cercetători din Republica Moldova. Țin să menționez despre importanța menținerii relațiilor moldo-japoneze, precum Universitatea de Stat de Medicină și Farmacie Nicolae Testemițanu din Republica Moldova, care au semnat un memorandum de înțelegere în luna martie 2021 cu Universitatea din Shinshu, Japonia, pe segmentul schimburilor academice și al cercetării științifice. De asemenea, anul trecut, la data de 14 mai 2021, Universitatea de Stat din Moldova a semnat un acord de colaborare cu Universitatea Tsukuba din Japonia privind organizarea mobilităților academice pentru studenții și profesorii ambelor instituții de învățământ superior. Totodată, profitând de această ocazie excelentă, aș dori să vă informez despre câteva noutăți optimiste și încurajatoare cu privire la știința și explorarea spațiului. În premiera pentru Republica Moldova, echipa de cercetători și studenți de la Universitatea Tehnică a Moldovei au proiectat și au construit un nanosatelit denumit TUM Nanosat, care în curând va fi transportat către Stația Spațială Internațională, de unde va fi lansat în spațiul cosmos prin intermediul unui sistem special al modului japonez numit Kibo. Kibo este un cuvânt din limba japoneză care înseamnă speranța. Acest proiect major pentru știința moldovenească este implementat în cadrul unui program sub egida Biroului ONU pentru afaceri spațiale și de către Agenției Aerospațiale Japoneze. Și eu consider lansarea primului nanosatelit moldovenesc drept un eveniment istoric în relațiile bilaterale moldo-japoneze. Momentan ne pregătim pentru un eveniment dedicat lansării nanosatelitului și personal doresc ca imaginile să fie văzute de cât mai mulți moldoveni, așa că vă rog să rămâneți aproape de ambasada noastră. Doamnelor și domnilor, dragi prieteni, tineri cercetători, Vă mulțumesc mult pentru atenție și vă doresc o zi cât mai fructuoasă. Vă mulțumesc pentru atenție.
Și noi vă mulțumim. Vă mulțumim și deoarece domnul profesor Hiroshi Amano este online, excelență, domnule ambasador și dragi studenți, elevi, tineri, cercetători, vom trece la engleză. So I would like to welcome online Professor Hiroshi Amano from Nagoya University and to thank him for his very kind contribution to the success of our events. Professor Hiroshi Amano 1 year ago, namely on June 10th, 2021, he delivered online a very interesting and important lecture, Economical Profit of Establishing a Regenerable Energy Society. And just a few weeks ago, on 24th of May 2022, he came online with an address in support of our efforts to restore peace in our region. He contributed to the success of the International Scientific Conference European Platform for Peace. The Academy of Sciences of Moldova succeeded to invite many well-known scientists from the world, and there was a contribution from 4 Nobel laureates, including Professor Hiroshi Amano. Dear Professor Amano, your contribution is highly appreciated by the scientific community of the Republic of Moldova. And here we have a special diploma of gratitude. I will read, is conferred to Professor Hiroshi Amano, laureate of Nobel Prize in Physics, Nagoya University, Japan, in recognition of his exceptional contribution to the development and promotion of science, as well as for outstanding public lectures presented at the Academy of Sciences of Moldova for the research community and students. We will ask the ambassador, the embassy of Japan in the Republic of Moldova to send this diploma to your address, or we can send directly from the Academy. Thank you so much. And news. In September next year, 2023, we will organize the 6th edition of International Conference on Nanotechnologies and Biomedical Engineering. And in collaboration with the groups from the Technical University of Moldova, including the group headed by Professor Victor Șontea, we will invite you, a special invitation for you to contribute to the 6th edition of the International Conference on Nanotechnologies and Biomedical Engineering. We hope that we'll continue our collaboration. I came back yesterday from Germany, participated in a very interesting international conference on intelligent materials. And I contributed with a presentation on intelligent, smart materials based on gallium nitride. I know that gallium nitride is your loved material, and I hope that we can, by joint efforts, contribute to the implementation of this unique material in many fields of research, including biomedicine. So, dear Professor Amano, thank you very much once again for your very kind contribution to lecturing here at the Academy of Sciences of Moldova. I can tell you that our young researchers, students, pupils, they love your lectures. Well, you are here a well-known expert, and we are waiting for you here in the Republic of Moldova. We will send an official invitation, no restrictions related to COVID anymore. And I hope that in the near future, it will be possible for you to fly to Europe and to pay, in this connection, a visit to the Republic of Moldova. So, dear attendees, Mr. Ambassador, with your permission, I will give the floor to Professor Hiroshi Amano, Nobel laureate in physics, Nagoya University, Japan. Professor Amano, you have the floor, please.
Thank you so much for the kind introduction and the invitation to the Republic of Moldova. Thank you so much. Can you see my slides?
So we see your slides. Mm-hmm.
Okay. Yeah, dear Ambassador, ladies and gentlemen, it is my great honor to attend this NanoMedTwin 2022 summer school. So first of all, I'd like to thank the organizers, especially Professor Ion Tiginiano, for giving me this opportunity. Yeah, today, as mentioned, I'd like to explain why the new material, the gallium nitride, is so promising and so interesting. And I do believe that we can draw a roadmap to realize a carbon neutral society with this material. Why new material research and development is indispensable is one of the examples is shown here. Yeah, in case of gallium nitride, we use it as the blue LED and the white LED lighting system. It contributes to energy savings. According to US Department of Energy, LED lighting will save 78 watts, meaning 22.9 petawatt hour for 18 years, and it corresponds to US dollar 890 billions. It's corresponding to 17 times 10 to the 12th Moldova lei. I'm not sure whether my pronunciation is correct or not, but it is huge savings we can expect with the new material, especially nanomaterial systems, materials and systems. LED is thought to be the fourth generation artificial lightings, fire, incandescent lamp, fluorescent lamp, and then LEDs. Incandescent lamp is efficient in infrared region, but it's not efficient in visible region. So the efficiency is limited to be lower than 20 lumens per watt. We can get only 20 lumens for 1 watt input. And their temperature is very high, over 3000 centigrade, so it's a short lifetime. Fluorescent RAM, it is a little bit better in terms of efficiency, but it is limited by the so-called Stokes shift loss. The excited electron, high energy electron excite mercury vapor, and mercury vapor emit deep UV light, 253.8 nanometer deep UV light, and which excite the phosphor materials. Then we can get the white light. But only the one photon can generate one photon. So energy loss is serious if we use the high energy deep UV light, deep UV photon. So efficiency is limited to be less than 120 lumens per watt. And it is fragile because of the glass tube. In case of LEDs, the solid state semiconductors, efficiency is limited only in principle by Joule loss. So efficiency is higher than 160 lumens per watt. And there is no essential issues to shorten lifetime. If we use the blue light for exciting yellow phosphorus, there is a Stokes shift loss, but the loss is much smaller than the fluorescent RAM, and it is tough material because of the solid state. If we look at the development of the LEDs at the initial stage, American researchers led by Professor Nikoloniak developed the first LED LEDs in 1962. And late Professor Jack Pankow developed MIS-type gallium nitride LEDs in 1971. However, the blue LED was very, very difficult. So I summarized the requirements for high efficiency blue LEDs. In the Christmas tree, you can see the blue, small blue light. And inside the LED lamp, you can find the LED chip. It is very, very small. And the requirement for efficient blue LED is high crystalline quality gallium nitride crystals, and both N-type and P-type gallium nitride, in addition to indium gallium nitride blue emitting layers. After several trials by the American and the European researchers, very famous researchers, they abandoned to continue the research in the late 1970s. However, my supervisor, when I was a student, Professor Isamu Kasaki, continued to perform the research on gallium nitride blue LEDs. The reason is, I can say that the blue LED research was driven by late Professor Isamu Kasaki's curiosity. The reason is, when he was a small child, his father gave him the many ore specimen. So he was interested in the different colors of the crystals. And when he graduated Kyoto University and entered the company called Kobe Kogyo, his first research subject is the development of the fluorescent phosphors for TV, brown tube TV systems. And he was so interested in the luminescence without heat. And then he moved to Nagoya University, and then he conducted the PhD research for growing germanium crystals. So he found the importance and the interest of growing semiconductor crystals. And then he moved to Matsushita, now Panasonic. He encountered with LEDs, which the American and European researchers developed. And he succeeded in commercializing the red and green LEDs. Business was so successful, so he received the company president award. However, he thought that he had to follow American and European researchers' patents to commercialize red and green LEDs. So he was seeking his originality. That's why he could continue the research on blue LEDs. He succeeded to fabricate MIS type LEDs, although it was so-called pressure Jack Pankow's type LEDs. And the luminescence was not enough. Luminance was not enough. So he wanted to improve the performance of his LEDs. However, the manager of the company, Matsushita, decided to stop the research and development of blue LEDs. So he had to move to Nagoya University in 1981. So his impression was, I went alone in the wilderness, because at that time, no one tried to do research on gallium nitride blue LEDs. I joined his group as the undergraduate student. When I saw the graduation research nitride-based blue LEDs, I was so excited, because at that time I was interested in the microcomputer system, now PC. And I used the brown tube, of course, but brown tube was too big. And if I could achieve blue LEDs, I would change the world. That's why I could concentrate on performing the blue LED research based on gallium nitride. The problem is, at that time, the Japanese university was very, very poor. So the research fund of Akasaki Laboratory was US dollar 23,000 US dollars, which corresponds to 440 kilo of Moldova lei. So students, including me, have to develop our own crystal growth reactors. This is our original handmade reactor. It is called MOVPE, metal organic vapor phase epitaxy reactor. So I had the experience of 3 years of trial and error, no success. I have tried more than 1,500 times, but I could not grow high quality gallium nitride crystals. But at the end of the master's course, Professor Sawaki taught me the story of boron phosphide on silicon. The boron phosphide growth on silicon was conducted by Professor Tatao Nishinaga before the Professor Isamu Akasaki's laboratory. So this story was very, very good hint for me. So finally, I succeeded to grow world's highest quality gallium nitride on the sapphire substrate at the time. And then I switched the gear to try to grow P-type gallium nitride. But many famous researchers abandoned P-type gallium nitride at the time. The reason is we need an acceptor to realize P-type gallium nitride. However, in case of gallium nitride, if we do acceptor impurities, donor level of native defects such as vacancy, nitrogen vacancy is automatically generated, which compensate the acceptor. It is called the self-compensation. But my impression of a self-compensation was only a poor excuse of the non-completion of P-type. So during the doctoral course, 3 years in case of Japan, I concentrated on trying to realize the P-type gallium nitride, but without any success. But after 4 years from the start of P-type challenge, I found my mistake. As an acceptor dopant, I used zinc, but according to the textbook, Phillips, Bonds and Bands in Semiconductors, I found that in case of boron gallium phosphide, magnesium is better than zinc in terms of the activation. So I switched the acceptor from zinc to magnesium, but magnesium doped gallium nitride itself is not P-type. So I tried the low energy electron beam irradiation treatment, LEBI for short. We had the crystal growth system developed by the students, but we didn't have the system for LEBI treatment. So our research partner now, Toyota Gosei, had the electron beam system. So after growing the magnesium doped crystals 1 hour by small scooter, I went to the Toyota Gosei and 7 hours for treatment, and then 1 hour by small scooter to go back to Nagoya University, and finally we succeeded the world's first P-type gallium nitride and PN junction LEDs. So how blue LEDs change our lives? The reason why you can use the full color smartphone is because of the emergence of blue LEDs. And according to Nobel Foundation, LED lamp holds great promise for increasing the quality of life for over 1.5 billion people around the world who lack access to electricity grids. Due to its low power requirements, it can be powered by cheap local solar powers. In 2015, after receiving the Nobel Prize, Mr. Gantumul, the Minister for Education and Science of Mongolia, visited us and gave me the word of gratitude. The reason is, according to him, for Mongolian people, the traditional lifestyle is the nomad life. Using the tent called gel, people are moving around. However, the life itself was very, very tough and difficult to continue, especially when the night comes. Incandescent lamp lifetime is very short. So the young Mongolian people abandoned the traditional lifestyle and tend to have the fixed housing. That's the social problem, he said. However, emergence of LED lamp changed the mind of young Mongolians. The LED lamp continued to emit light whole night. So in 2016, when I visited one of the Mongolian family who continued the nomad life, when I saw the LED lamp inside the girl, I was so happy to see that. Yeah, and this material is not useful for LED lamp, but also it is very, very useful for transistors. We will save another 10% electricity consumption by replacing silicon power devices to gallium nitride power devices. Let me explain why it is so important. According to the Intergovernmental Panel on Climate Change 6 assessment report, it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and the biosphere have occurred. So, climate change is already affecting every inhabited region across the globe, with human influence contributing to many observed changes in weather and climate extremes. From 1950s, there was many hot extremes, heavy participation, and agriculture and ecological drought. And more seriously, possibility of energy shortage. UK Prime Minister Boris Johnson has trumped the EU's addiction to Russian oil and gas during an exchange in Parliament over Russian invasion of Ukraine. He said Europe addicted to Russian gas. But the situation is very similar in Japan. In Japan, 5.4% of oil and 8.3% of LNG and 12% of coal were imported from Russia. So I think it's time to replace fossil fuel-based energy system to renewable energy-based system. So how long does it take to change the energy systems? So we estimate how much renewable energy is necessary for Japan to become a carbon neutral country. Our target is estimated to be 700 gigawatts. Now it is 1/10, 70 to 80 gigawatts. Okay, but in Japan, due to the feed-in tariff system, annual growth rate of renewable energy is very high, 18%. And if we continue such an increase of renewable energy system, average annual growth of 10.6% is enough. Okay. And so we can realize 700 gigawatts by 2043 if average annual growth rate of 10.6% is continued or achieved. And we don't need Russian fossil fuels from 2025. So within 2 or 3 years, we don't need the Russian gas or oils. Okay, maybe you heard that there is a very serious problem or shortage of semiconductor devices. And in this case, semiconductor devices means a silicon-based device. So I'd like to mention that let's replace silicon power devices to wide bandgap semiconductors. The reason is, of course, the silicon market is huge. US dollar 478,000 million. And the market size of the power device is very small, US dollar 29,000 millions. So market size is 16 to 1. However, the cost for developing a silicon device is very, very expensive. In case of logic, we need a very narrow EUV system, extreme UV lithography system. It costs more than 100 million euro. But in case of gallium nitride power device, we need only old I-line stepper, 100 nanometer, and it costs less than 5 million euro. So investment cost is 20 to 1. So small investment and the big payoff can be expected if we invest to the new material and the systems. Application of gallium nitride power devices in electric vehicles is shown here. This is the Tesla, and all the electric vehicles, the battery is used for driving. The battery is the direct current, DC power source, but the motor is the AC motor. The reason is the AC motor is much more efficient than the DC motor. So we have to change the DC power to AC power. And the principle is very simple. We prepare the 4 switches and the battery and motors. At the first period, we switch this switch and this switch on. So current flow from left to right. And the second period, we switch this and this on. So the current flows from right to left. Then we can realize the AC power from DC source. And as the switches, we use the transistors like this. It's an NPN junction. The current flows from P to N, but never flows from N to P. So in these transistors, if there is no signal, the current never flows. But if we input the signal to the gate, positive voltage, the electrons accumulate, and then it changed from P-type to N-type at the surface, and then current flows. So we can control the on and off by a computer system. And what limits the efficiency of inverter is the red line shows the current and the black line shows the voltage. At off state, the voltage is high and there's no current, so there is no loss. However, at on state, the current flows and the voltage could not be zero. There is small amount of voltage. Therefore, there is a conduction loss due to the small voltage and the large current. And also during switching, we have the switching loss. Why gallium nitride next generation semiconductors are so attractive? Because the breakdown field is very, very high, 10 times higher than the conventional silicon. So we can reduce the size of the chip to 1/10. So we can reduce the conduction loss by 1/10. In addition, we can also reduce switching loss by using gallium nitride, because gallium nitride transistor can be operated with much, much higher speed. Then we realized 65% reduction of inverter loss. It is demonstrated in 2019. He is the former Minister of Environment, Koizumi, and he's the president of Toyota Motors, Akio Toyota. Using this gallium nitride inverter system, we can reduce the size of inverter to a half of the weight and half of the volume compared with the silicon carbide inverter. In Tesla 3, the inverter shape is, as you know, this is American map, but by using the gallium nitride inverter, we can realize the Japan map inverter. We are continuing the research under one roof, comprehensive team of from crystal growth through the system applications. Okay. For example, he's from University of Cambridge, he's from Denso, University of Tsukuba, NEC, Kyoto University, Toyota Central Research and Development Laboratories, Shimane University, Toyota Gosei, ICE, and SHERP. And these specialist team will realize any kind of applications from electric vehicle to airplanes. And also, we can use to new communication system, 5G and post-5G system. And we also establish gallium nitride research and development strategy management teams. He's from New Japan Radio, Panasonic, NEC, and Panasonic. These private companies team will lead the strategy and management of the gallium nitride research and development. In addition, we establish a consortium. Now, 51 companies, 21 universities, and 2 research institutes join the gallium nitride consortium. And we are conducting the clean room operation. This is dedicated to fabricate gallium nitride devices. The size is not so large, 1,000 square meters, but the important thing is there are 8 members, including 2 PhDs from the companies, not the university staff, but the company staff. And most important thing is their salary is paid by Nagoya University. So we can keep confidential technologies and provide the nano system, nano device to the person who are interested in our activities. So we are conducting the new program, Ministry of Education, Innovative Power Electronics Technologies till 2025. And we are in the power device team, and we are collaborating with the circuit system team, Professor Takahashi of Tohoku University and Professor Wada of Tokyo Metropolitan University. And also we are collaborating with passive component system teams, Professor Mizuno of Shinshu University, Professor Okamoto of NIMS, and Professor Habazaki of Hokkaido University. And also we are collaborating with the next generation technology team, power device and common technology team, circuit system, and the passive component team. And in this program, our services is to provide packaged devices. This is the example of the packaged devices, gallium nitride junction barrier Schottky diodes. As shown in this view graph, you can see the Nagoya U. This is made by Nagoya University. This is quite new to the university in Japan. It was very difficult to provide a packaged device to other teams. And our goal of this project is provide packaged vertical MOSFET for new system development. So we will provide a proof of concept level products of gallium nitride based devices and modules to the person who is willing to establish a supply chain of the systems. And our final goal is to contribute to develop a carbon neutral country by new semiconductor materials. And if you are interested in our activity, please do not hesitate to contact me. My email address is shown here. So I do believe you will play a key role in establishing the future of Moldova and contributing to develop carbon neutral world. Future is yours. So thank you so much for your kind attention.
Yeah, dear Professor Amano, thank you for the very, very interesting presentation with a lot of information. And I think that there will be also some questions. I would like to underline that besides of higher power devices, gallium nitride is also very good for higher frequency as a higher frequency material for higher frequency devices. And we succeeded to develop the so-called aero gallium nitride. Aero gallium nitride is a three-dimensional nano architecture with the walls of these highly porous materials of about 10 nanometers thickness of the wall. It's ultra lightweight material, highly porous, and it shields perfectly electromagnetic waves in both gigahertz and terahertz regions of the spectrum. I will send you a few papers, just recent papers. We published these results, and in my opinion, aero gallium nitride is a very promising material for for space applications, because it shields very perfectly electromagnetic radiation in both gigahertz, terahertz regions of the spectrum. Along with this, I would like to note that gallium nitride is a biocompatible material. And we demonstrated that gallium nitride hollow nanoparticles penetrate into living cells. And so we can use external electric and magnetic fields to have a control upon the behavior of the cells, upon the vital processes happening in the cell. With the electric field here, it's clear, but a magnetic field we can apply in the case we dope these nanoparticles with magnetic elements like iron. Now my question is, your opinion as an international expert in gallium nitride, probably the strongest expert in gallium nitride at the international level, your opinion concerning the use of gallium nitride in such fields, such space applications or in biomedicine?
Okay, thank you so much for the very important questions. For space applications, we are now trying to develop new high power, not microwave, but millimeter wave and terahertz wave energy transmission system by gallium nitride. And we are just starting to collaborate with JAXA. JAXA is the research organization in Japan for space applications. And we have developed very high power microwave transmission system as a first step. And then next, we will try to develop a millimeter wave or terahertz wave energy transmission without any wire, wireless energy transmission system. And also, of course, we can use it as the information transmission, the wireless information transmission. And also, some other group are trying to transfer energy by light or lasers. Laser energy transmission system is in progress. So for energy transmission, yeah, we are already trying to develop for the future space applications. And for bio applications, we are interested in the wearable systems, and the nitrides can be used. Nitride transistors can also be used for some sensors, and also the information transmission to the internet or the servers. So for the bio applications or biomedical applications, the nitrides can be used as the several sensors and also the information transmission systems. Okay.
Thank you so much. Now I would like to ask the students attending online and in the Blue Hall of the Academy, if any questions, please. In case of online, please tell us. There are questions actually in chat. Who can read in chat? Tudor, maybe you can. Professor Amano, can you read the questions that we have in chat?
Yes, thank you for the question. Dear Dr. Hiroshi Amano, there is not enough political will around the world to understand the importance of all the things you were stating on climate change. Oh, thank you so much. Very important question and suggestion. Yes, yes, you are right. At present, there are many things that should be solved as possible. So many politicians want to pay money for the things we should solve first. In comparison, in case of the climate change, and not all the politicians are concentrated on this matter, but we do believe, or I do believe, that the climate change is also very, very serious, and we should solve as soon as possible. So the things we should do is to demonstrate how important this materials research and development is important. So we are trying to provide the proof of concept level devices and systems, and we are trying to provide the systems to the company or the person who are interested in starting the new companies. For us, the penetration of the devices to all the people, people is very, very important, because one device is not sufficient to reduce the energy savings. We have to request all the people to use the much efficient systems. So that's why we are collaborating with the several companies who are interested in the carbon neutral or the reduction of the energy. So our activity is to provide proof of concept devices to not the politician, but the person who are trying to penetrate the devices to the people all over the world. Okay.
Yeah, thank you so much. Of course, in case of problems that nowadays the humanity actually should overcome, science should come with solutions. And there was the Glasgow Forum, International Forum in November last year, where world leaders actually recognized that the solutions should come from scientists, and therefore, of course, science should be supported internationally. During our conference, the International Platform for Peace, so a Nobel laureate underlined that actually scientists are prepared to tell the truth about problems, and while politicians actually they will comment looking at people who will vote for them. That's clear. Therefore, the scientists should play the major role. Yeah. And we can succeed in identifying solutions for all problems of the civilizations only by joining efforts and of course at the international level by collaboration. And dear Professor, I would like to thank you very much for your lecture today, a very interesting lecture with a lot of information. I think that it's very useful for all of us, for students and also for the experts in the field. I would like also to thank His Excellency Ambassador of Japan to Moldova for his attendance of this lecture. We enjoyed together your presentation, and of course We will wait for you here in Moldova. Please identify a possibility to come to Moldova to pay a visit. Moldova is a nice country, a beautiful land, very nice traditions, and of course we will do our best that you will enjoy the Republic of Moldova. Thank you so much. We wish you good health and success in the future.
Thank you so much. Thank you.
Ladies and gentlemen, we will have 5-7 minutes